The shell had already passed through the Sherman's side armor. Inside, fragments crossed a compartment, crowded with ammunition. Propellant ignited before the fuel tanks became the central danger. The crew had only seconds. This was the weakness behind the Sherman's darkest wartime reputation. It was not simply a gasoline problem, it was an ammunition problem. Early Shermans carried many main gun rounds along their upper hull sides. These spaces were called spunsons. They offered convenient storage beside the fighting compartment. They also placed cartridges behind armor frequently exposed to enemy fire. A penetrating round did not need to strike a fuel tank. Hot fragments could tear open a cartridge case. They could ignite the propellant packed behind the shell. Once burning began, nearby rounds added more heat and pressure. The fighting compartment could become impossible to occupy. Crews understood the danger long before historians debated the statistics. A burning tank was also difficult to recover. Fire destroyed wiring, instruments, seals, ammunition, and hardened components. Even a repairable penetration could become a permanent vehicle loss. The Sherman's reputation therefore grew from something crews could plainly see. Knocked-out tanks often burned. Yet the visible result concealed the exact mechanism. The Sherman used several different engines during its production life. Some burned gasoline. The M4A2 used diesel fuel. That difference encouraged a simple explanation for every burned wreck. Gasoline tanks burned because gasoline was dangerously flammable. The answer sounded convincing. It was also incomplete. British battlefield examinations in North Africa shifted attention toward ammunition placement. Investigators studied penetrations and the damage found inside disabled tanks. They found that exposed cartridges presented a critical ignition risk. The location of those cartridges mattered more than popular memory suggested. American engineers first pursued a limited correction. Armor plates were added outside vulnerable ammunition positions. Some exposed rounds were also moved into better protected containers. This became known as the quick fix. The modification addressed an obvious path through the hull side, however. It did not redesign the entire internal arrangement. A stronger answer required moving the ammunition itself. That meant changing a tank already being built in enormous numbers. The eventual redesign placed most main gun ammunition beneath the turret floor. This was lower in the hull and less exposed to common penetrations. The rounds sat inside protected racks surrounded by liquid-filled jackets. The cartridges were not simply submerged in water. Each round remained accessible inside its own storage space. The surrounding mixture was intended to suppress small ignition sources. It could also slow the spread of heat between damaged cartridges. This arrangement became known as wet-stowage. The famous liquid was only part of the solution. The deeper advantage was location. A projectile crossing the upper hull now had fewer exposed cartridges to strike. Steel covers added another barrier between fragments and propellant. The redesign attacked the fire chain before it could accelerate. First came penetration, then fragments, then damaged cartridge cases, then burning propellant. Wet-stowage tried to interrupt that sequence near its beginning. The change demanded far more than installing several new boxes. The turret basket and fighting compartment required extensive rearrangement. Access to ammunition had to remain practical during combat. Crew movement could not become dangerously restricted. Production lines also had to absorb the redesigned hull. New large-hatch Sherman models began receiving the system during 1944. The feature appeared across specific later production variants. It was not present in every Sherman. It was not retrofitted universally to older tanks. That distinction is essential. Photographs of different Sherman versions often conceal major internal differences. Two tanks could appear broadly similar from a distance. One might carry exposed ammunition along its sides. The other kept most rounds beneath an armored floor. Their chances after penetration were not necessarily the same. Later wartime evidence suggested a dramatic reduction in ammunition fires, yet even that result requires careful interpretation. Better racks arrived alongside other design changes and growing crew experience. A tank could also receive repeated hits after being disabled. Enemy gunners often continued firing until flames confirmed the kill. Burned wrecks therefore did not provide a perfect laboratory. Still, the engineering direction was unmistakable. The Sherman did not become impossible to burn. No wartime medium tank achieved that. Instead, one internal rearrangement removed a major source of catastrophe. The most important protection was not thicker frontal armor. It was hidden beneath the crew. The Sherman entered British service during the campaign in North Africa. Its arrival came at a critical moment in 1942. British armored units needed a reliable tank with useful firepower. The new American vehicle offered both. Its 75mm gun could engage armor, field positions, and anti-tank guns. The turret carried 3 men. The commander could observe instead of loading the main gun. Mechanical reliability also compared favorably with several earlier British designs. These strengths made the Sherman valuable. They did not make it invulnerable. German anti-tank guns could penetrate its armor under realistic battlefield conditions. When penetration occurred, the internal arrangement became crucial. Early production Shermans stored ammunition in several locations. Large racks occupied the hull sponsons above the tracks. Additional rounds were carried around the fighting compartment. This distributed arrangement provided access to a substantial ammunition supply. It also created several exposed targets inside the tank. The danger was not limited to a direct shell impact. A penetrating projectile produced a cone of fragments behind the armor. Pieces of the projectile could join fragments broken from the hull itself. These fragments moved through the compartment at dangerous speeds. A cartridge case offered little protection against them. The shell inside was not always the first material to ignite. The propellant charge behind it presented the immediate fire hazard. Tank ammunition used combustible propellant contained within a metal cartridge case. Puncturing that case could expose the propellant to hot fragments. Ignition produced an intense fire. It did not always create an instantaneous explosion. Instead, burning charges could fill the compartment with flame and smoke. Nearby cartridges might then ignite in sequence. This distinction mattered to investigators. Fuel was capable of burning fiercely. However, fuel tanks were not the only source of destructive fires. Ammunition occupied positions more directly exposed to many side penetrations. The evidence demanded a closer examination of what happened after armor failed. British operational research teams studied damaged Shermans from desert fighting. They compared penetration locations with ammunition storage positions. The relationship was difficult to ignore. Hits near the sponson racks frequently produced serious internal fires. The findings challenged the easiest explanation. Changing the engine alone would not remove exposed propellant. A diesel Sherman could still suffer an ammunition fire. A gasoline Sherman could survive if its ammunition remained protected. The decisive question concerned the path taken by penetrating fragments. Engineers therefore needed more than thicker fuel tanks. They needed to reduce the ammunition's exposure. The first response did not involve a completely new hull. Existing production made rapid changes difficult. Factories were already delivering tanks in enormous quantities. Units overseas needed replacements immediately. A perfect redesign arriving late could save nobody in the present. The Quick Fix program attempted a practical compromise. Additional armor plates were welded onto the hull sides. Their positions corresponded with vulnerable ammunition racks inside. The plates are clearly visible on many surviving early Shermans. They appear as rectangular patches attached to the upper side armor. Similar protection was added near vulnerable turret ammunition. Crews and workshops could recognize the intended purpose immediately. More steel stood between enemy fire and the cartridges. Yet the solution had serious limitations. A plate covered only a defined area. Enemy rounds did not arrive at one predictable angle. Fragments could travel beyond the plate's outline. A powerful anti-tank projectile might penetrate both layers. The ammunition itself remained high inside the fighting compartment. The Quick Fix treated the route toward the hazard. It did not remove the hazard from that route. Some ammunition was also relocated into armored containers. This improved protection for particular rounds. However, the basic dry stowage layout remained recognizable. The Sherman still carried much of its ammunition beside the crew. Battlefield urgency had produced an intermediate answer. It bought time. It also revealed the direction of the final solution. If side armor could not guarantee protection, exposure had to be reduced internally. The safest available space was lower in the hull. Tracks, suspension, and road wheels partly screened that region. The hull floor also sat below many common lines of fire. Moving the cartridges there would change what fragments encountered after penetration. It would also force engineers to rebuild the Sherman's internal geography. That was the price of solving the real problem. Moving the ammunition downward sounded simple on a drawing board. Inside a working tank, it affected almost everything around it. The Sherman's turret rotated above a circular basket. Crewmen occupied this moving structure while the tank crossed uneven ground. The loader needed rapid access to heavy cartridges during an engagement. The driver and assistant driver needed clear escape routes. Control cables, seats, radios, and equipment competed for limited space. Ammunition could not merely be placed wherever armor offered protection. It had to remain reachable. The new arrangement concentrated most rounds beneath the turret floor. Armored covers separated the racks from the fighting compartment. The loader reached them through openings in the floor. This removed the tall ammunition racks from the upper hull sides. A penetrating fragment now faced a smaller chance of finding propellant there. The road wheels and suspension provided additional material outside the lower hull. They were not designed as armor. However, they could disturb fragments and alter some projectile paths. The lower racks also benefited from their position beneath the turret structure. This was passive protection created by geometry. Around the cartridges sat liquid-filled compartments. The mixture included water and antifreeze compounds. Antifreeze helped the system remain useful during severe winter conditions. The liquid did not make ammunition harmless. It could not extinguish every large propellant fire. It was intended to suppress heat and small ignition sources around damaged rounds. This gave the design its wet-stowage name. The name later overshadowed the more important structural change. Liquid jackets were visible in diagrams and easy to explain. Moving ammunition below the floor was less dramatic, yet location determined whether fragments reached the cartridges at all. Avoiding ignition was better than fighting it after it began. The redesigned storage also demanded different loading habits. Ready access mattered most during the first moments of combat. Opening protected floor racks required time and physical effort. The loader worked inside a moving, noisy compartment. He handled long cartridges while the turret changed direction. A protective cover could become an obstacle if poorly positioned. Designers had to balance safety against sustained firing speed. A tank surviving penetration still needed to function as a weapon. The new layout therefore preserved a small ready supply near the gun. These rounds offered immediate access. They also meant that no internal arrangement removed every exposed cartridge. Survivability was improved through risk reduction. It was never absolute. Crew practice could weaken the system further. Tankers often carried additional ammunition before difficult operations. Extra rounds promised longer fighting without resupply. They could also end up outside protected racks. Loose cartridges might be placed on the hull floor or other convenient surfaces. That restored hazards the redesign was intended to remove. A Wet-Stowage Sherman only gained its full advantage when crews used it correctly. This tension appeared across armored warfare. Factory protection competed with battlefield convenience. A loader under pressure valued any round he could reach quickly. A commander anticipating prolonged combat wanted every available cartridge aboard. Neither desire was irrational. Both could increase the consequences of penetration. Maintenance created another complication. The liquid jackets required inspection. Damage, leaks, freezing conditions, or neglected servicing could affect their intended function. The system added tasks to an already demanding vehicle, however. Its fundamental protection did not disappear when liquid was absent. The ammunition still remained low and covered. This helps explain later doubts about the liquid itself. Engineers questioned how much improvement came from suppression. They could not ignore the benefit created by relocation and armor. Wet-stowage was therefore not one invention. It combined several protective ideas. Remove cartridges from exposed side racks. Place them lower in the hull. Cover them with armor. Surround them with fire-suppressing liquid. Control access through the turret floor. Each measure interrupted a different part of the damage sequence. Together, they changed the crew's survival environment. The redesign appeared in new production Sherman variants during 1944. Large hull hatches provide one external clue on many examples. The letter W in later designations identified wet ammunition stowage. However, wartime records and photographs still require caution. Field modifications could alter a tank's appearance. Different factories introduced changes at different moments. Turrets and hulls could also be replaced during repair. A visible armor patch did not automatically identify every internal detail. The variant must be established before judging its vulnerability. That problem has distorted many later comparisons. Early and late Shermans are often treated as one unchanged machine. They were not. The tank that fought in North Africa differed meaningfully from later production vehicles. Its silhouette remained familiar. Its internal risk had changed. The first Wet-Stowage Shermans reached production before most American troops landed in Normandy. Their arrival did not immediately replace every earlier tank. Armored units entered France with mixed equipment histories. Some vehicles had trained in Britain for months. Others arrived later as replacements. Production dates, shipping schedules, and battlefield losses shaped each unit's inventory. The improved design therefore entered combat gradually. Among 75mm tanks, Wet-Stowage appeared in later M4A1 and M4A3 production. These vehicles used the redesigned large hatch hull. Their front armor differed from the earlier small hatch arrangement. The ammunition racks beneath the turret floor were the more important internal change. Shermans armed with the 76mm gun also received Wet-Stowage. Their ammunition dimensions required a distinct rack arrangement. They should not be treated as identical to the 75mm installation. The 76mm turret came from a separate development path. Its larger gun changed balance, working space, and ammunition handling. The W designation identified Wet-Stowage within these later model names. It did not identify one universal Sherman configuration. The M4A2, M4A3, and M4A1 differed mechanically. Their engines and hull construction were not interchangeable details. Some used welded hulls. The M4A1 used a rounded cast hull. The M4A2 used twin diesel engines. The M4A3 used a gasoline-powered Ford engine. All could appear in discussions about Sherman fires. Only careful variant identification keeps those comparisons meaningful. The United States Army favored the M4A3 for its later wartime forces. British, Canadian, French, Polish, and Soviet formations received other Sherman types. Their ammunition arrangements varied with model and production period. A Soviet M4A2 with a 76mm gun could have Wet-Stowage. An earlier British Sherman with a 75mm gun might not. The shared Sherman name concealed those differences. Normandy exposed tanks to a harsh combination of threats. German anti-tank guns covered roads, villages, and field boundaries. Panzerfaust weapons became especially dangerous at close range. Mines damaged tracks and stopped vehicles inside engagement areas. Artillery fragments could enter open hatches or strike thinner surfaces. Even a tank surviving its first hit might remain under fire. Crews often had to escape while nearby vehicles blocked movement. In these conditions, ammunition protection could not prevent penetration. It could change what followed. A dry-stowage tank presented cartridges along the path of many side hits. A Wet-Stowage tank offered fewer exposed rounds in that zone. This created time. The difference might be measured in seconds rather than armor thickness. A crew could recognize the hit. The commander could order evacuation. Hatches could be opened before flames filled the compartment. Not every crew escaped. Not every protected tank avoided fire. However, delaying ignition could separate a survivable loss from a catastrophe. Battlefield reports also reveal why simple burn percentages require caution. Investigators usually examined tanks after the fighting ended. They could identify penetration holes and visible fire damage. They could not always reconstruct the precise sequence of hits. A tank might receive one disabling penetration. German gunners could then fire again. The later projectile might ignite ammunition inside an already abandoned vehicle. The wreck would appear as a burned combat loss. That did not prove the first hit caused an immediate fire. Recovery practices added another bias. An unburned tank could often be repaired. Its penetration might be patched and damaged components replaced. A burned tank was more likely to remain where investigators found it. Photographs naturally favored dramatic wrecks. Flames and blackened hulls created memorable evidence. Repairable vehicles disappeared into workshops. The surviving image record therefore exaggerates destruction. This does not make early Sherman fires imaginary. The vulnerability was real enough to drive a major redesign. It means the historical question must be framed carefully. The useful comparison is not whether any Sherman could burn. Every tank carried fuel, ammunition, oil, and electrical equipment. The useful question concerns the probability of fire after armor penetration. That is where protected lower storage changed the result. It addressed the event crews feared most. The armor had already failed. The tank might already be lost. The remaining battle was for time. Wet-Stowage gave the crew more of it. By 1945, investigators had accumulated evidence from several theaters. The emerging comparison appeared dramatic. Reports associated dry-stowage Shermans with burn rates between 60 and 80% after penetration. Wet-stowage vehicles were associated with rates near 10 to 15%. Those figures became the redesign's most famous evidence. They also require careful boundaries. They did not describe every Sherman ever hit. They did not measure the chance of a tank being penetrated. They addressed fires among particular samples of penetrated vehicles. Different weapons, angles, units, and battlefield conditions affected each case. The samples were not identical laboratory experiments. A percentage could summarize observed wrecks. It could not recreate every impact. However, the gap was too large to dismiss as statistical noise. Later, ammunition arrangements were consistently linked with fewer fires. The evidence supported the central design decision. Removing cartridges from the upper side racks worked. The liquid surrounding the new racks was harder to evaluate separately. Several changes had entered the tank together. Ammunition moved downward. Armored covers protected it. The number of exposed rounds decreased. The hull arrangement changed. Crew practices also evolved through combat experience. No battlefield survey could isolate each feature perfectly. The system succeeded as a package. Popular memory reduced that package to water. This created a second myth. Some later accounts imagined shells floating inside flooded containers. Others treated liquid as a magical shield against any ammunition fire. Neither picture described the installation accurately. The cartridges rested inside individual tubes within jacketed racks. Liquid occupied spaces around those tubes. A severe direct hit could still defeat the protection. Propellant could still ignite. Rounds carried outside the racks remained exposed. The Sherman had become safer. It had not become fireproof. The opposite myth proved equally persistent. According to that story, gasoline engines made every Sherman unusually combustible. The tank supposedly ignited from almost any penetrating hit. That explanation ignored diesel-powered models that could also burn. It ignored ammunition findings from damaged vehicles. It also ignored the improved fire performance of later gasoline-powered Shermans. The M4 remained gasoline-powered. Its wet-stowage version still showed the value of protected ammunition placement. Fuel type mattered in particular circumstances. Gasoline vapors could ignite. Damaged lines could spread burning fuel. Engines and fuel tanks remained hazards in every armored vehicle. But fuel did not explain the full pattern. A penetrating hit near a spunsen ammunition rack created a more immediate route to disaster. The myth survived because burned tanks all looked similar afterward. Flames destroyed the evidence people needed to distinguish causes. A blackened engine deck suggested fuel. A missing turret suggested ammunition. Real damage could involve both. Heat from one fire could ignite another material later. Ammunition might burn after fuel ignited. Fuel might ignite after ammunition began burning. Investigators needed penetration maps and internal examinations. Observers looking at photographs rarely had either. Language also shaped the reputation. British crews sometimes used grim nicknames for tanks believed to burn easily. Post-war writers repeated them without consistent context. A memorable nickname traveled farther than an ordnance report. It compressed different variants, years and armies into one image. The result treated the Sherman as a single fixed design. Production history tells another story. The tank changed continuously. Factories altered armor, hatches, turrets, sights, suspension components, and ammunition storage. Field workshops added further modifications. A Sherman photographed in Tunisia during 1943 was not equivalent to one built late in 1944. Their names were related. Their internal protection could be fundamentally different. The wet-stowage story also challenges a common expectation about tank development. Survivability is often imagined as an armor contest. More protection supposedly means thicker steel. Thicker steel adds weight. Added weight strains the engine, transmission, suspension, and bridges. Internal rearrangement offered another path. Engineers could reduce the consequences of penetration without making every armor plate thicker. They protected the material most likely to turn damage into catastrophe. This principle reached beyond the Sherman. Modern armored vehicles separate ammunition from crews whenever possible. Some use isolated compartments and controlled escape paths for blast pressure. The wartime Sherman lacked those later systems. Yet its redesign followed the same underlying logic. Armor may eventually fail. Survival then depends on what the projectile encounters inside. The safest ammunition was not ammunition surrounded by the most dramatic technology. It was ammunition fragments were less likely to reach. For a Sherman crew, protection after penetration began with physical layout. 5 men occupied a space filled with machinery and stored equipment. The commander and gunner worked on the turret's right side. The loader occupied the left. The driver sat in the front left of the hull. The assistant driver sat to his right. Each man needed a usable path out. Early Shermans complicated escape through their smaller front hatches. The driver and assistant driver sat beneath projecting sections of the front armor. Their hatch openings were restricted by the surrounding structure. Later large hatch hulls changed that arrangement. The front armor became a cleaner, continuous slope. Larger openings improved access for the two hull crewmen. This development accompanied wet ammunition storage on later production tanks. The changes addressed different threats. Lower ammunition reduced the chance of a rapid internal fire. Larger hatches improved the chance of escaping one. Together they strengthened crew survivability after armor failure. Turret crewmen faced their own obstacles. The commander had a hatch above his position. The loader did not receive a dedicated hatch on many early turrets. He might need to cross the fighting compartment during evacuation. The main gun's position could obstruct movement. A wounded crewman could narrow an already confined route. Smoke could remove visibility within seconds. Even an unlocked hatch might become difficult to find. Later, turrets added a loader's hatch. Again, this was not thicker armor, it was a change in escape geometry. A small opening could influence whether several men survived. Fire speed determined how much these details mattered. A slow engine fire might provide warning. A propellant fire inside the fighting compartment could spread immediately. Flame, pressure, and toxic smoke attacked the crew together. Heated cartridges might ignite one after another. The tank could remain dangerous after everyone escaped. Reducing exposed ammunition interrupted that escalation. It also protected rescuers and recovery teams from some secondary fires. The benefits extended beyond survival. An unburned Sherman could remain a military asset. Maintenance crews assessed damaged armor, controls, weapons, and running gear. Some tanks returned to service after significant repairs. Others provided usable parts for vehicles still operating. A fire destroyed much of that value. Heat altered the strength of armor and mechanical components. Electrical insulation disappeared. Optical equipment cracked or became contaminated. Rubber seals, hoses, and wiring burned throughout the hull. A penetration had become a total loss. Wet stowage improved the possibility of recovery. The tank might still be abandoned during combat. Its gun might be damaged. Its crew might never return to it. Yet an unburned hull offered options after the battlefield moved forward. This mattered in a campaign driven by replacement and repair. American armored units could draw upon enormous industrial production. They still depended on workshops, transporters, spare parts, and trained crews. A repaired tank reached service faster than a new vehicle crossed the Atlantic. A surviving crew carried even greater value. Its members understood radio procedure, maintenance habits, and unit tactics. They had learned how terrain concealed anti-tank guns. They recognized the sound and effect of incoming fire. Replacing that experience was difficult. The redesign therefore protected more than 5 individuals. It helped preserve a trained team. Survivability statistics can obscure this human dimension. A tank listed as knocked out might return days later. A crew listed as surviving might still include wounded men. A burned vehicle could be empty because its crew escaped before later hits. Records rarely capture every second inside the hull. The engineering objective remained clear despite this uncertainty. Create distance between penetration and catastrophe. Distance could be physical. The cartridges moved away from vulnerable side armor. It could also be temporal. Protected racks delayed the spread of fire. That delay opened choices. The driver might halt the engine. The commander might assess whether movement remained possible. The loader might leave through his own hatch. Crewmen might help an injured companion. No rack guaranteed those outcomes. It made them more achievable. This is why the redesign cannot be judged only by tank losses. Its most important result was often invisible. A crew climbed out. A damaged hull did not burn. A recovery vehicle returned after dark. The Sherman entered a workshop instead of a scrapyard. Nothing in that sequence produced a dramatic battlefield photograph. That was precisely the point. Factory engineering could only protect ammunition stored in its intended location. Combat repeatedly encouraged crews to alter that arrangement. A Sherman carried a defined number of rounds in protected racks. A unit expecting heavy resistance might want more. Resupply could become uncertain during a rapid advance. Trucks struggled along damaged roads behind armored columns. Bridges failed under traffic. Mines and artillery delayed supply vehicles. A commander could not assume ammunition would arrive during battle. Extra rounds seemed like practical insurance. They were also difficult to secure. Crews placed cartridges wherever space remained available. Some rested on the hull floor. Others occupied open areas near the turret basket. These rounds lacked the protection of the wet racks. Fragments reaching them could restore the original fire hazard. Loose ammunition also complicated movement inside the tank. A cartridge could shift while crossing rough ground. It might obstruct the rotating turret basket. It could delay access to a hatch. The safest factory layout depended upon disciplined stowage. Crews understood the risks. They also understood the danger of running out of ammunition. This was not careless behavior in every case. It was a trade made under uncertainty. Different missions changed the calculation. An attack against fortified positions demanded large quantities of high-explosive ammunition. A meeting with German armor required armor-piercing rounds. Smoke shells supported movement and marked targets. No crew knew the exact mixture it would need. The Sherman 75mm gun was valued for this versatility. Its ammunition supply supported many tasks beyond fighting tanks. That operational strength increased pressure to carry additional rounds. The protected racks also slowed access after the ready supply was exhausted. The loader had to open floor covers and lift cartridges upward. He worked while the turret moved and the tank changed direction. Dust, spent cases, personal equipment, and damage could interfere. A round stored within immediate reach always seemed attractive. Convenience and protection pulled in opposite directions. Training tried to establish the proper balance. Crews learned designated storage positions and loading procedures. Experienced units also developed local habits. Some removed equipment they considered unnecessary. Others added tools, water cans, track blocks, and personal gear. Every object occupied scarce space. External stowage reduced internal clutter but created other vulnerabilities. The tank seen in a manual rarely matched the tank seen after weeks of combat. This complicates historical evaluation. A wet-stowage designation describes the vehicle's designed arrangement. It does not prove every cartridge was inside a protected rack. A tank could burn because additional ammunition had been carried improperly. The wreck alone might not reveal that decision. Fire consumed packaging and altered internal evidence. Investigators sometimes had to rely on crew testimonies. Survivors could be wounded. Shocked or uncertain about the sequence, the best reports, therefore, combined several forms of evidence. They recorded penetration locations. They examined remaining ammunition racks. They noted fuel damage and internal burning. They interviewed crews when possible. They compared multiple vehicles rather than trusting one spectacular example. This approach exposed another weakness in popular comparisons. Photographs often place a burned Sherman beside an intact German tank. The image invites a conclusion about design quality, yet the intact tank may have been abandoned mechanically. The Sherman may have received repeated fire. Neither vehicle's ammunition condition is visible. A single photograph cannot establish a burn probability. German tanks also suffered ammunition fires after penetration. They carried propellant, fuel, hydraulic fluid, and lubricants. Their internal layouts created different vulnerable paths. No major wartime tank escaped the basic physics. Comparing national stereotypes hides those mechanisms. The relevant questions are specific. Where was ammunition stored? Which armor surfaces protected it? What projectile path reached it? How quickly could fire spread? Could the crew escape? Could the vehicle be recovered? These questions produce useful comparisons without inventing a perfect tank. They also explain why a modest internal change mattered so much. Wet stowage did not improve the Sherman's gun penetration. It did not make its armor immune to German weapons. It did not eliminate mechanical failures or mines. It addressed one narrow failure chain. That chain happened to decide whether many damaged tanks became burning wrecks. The system worked best when crews respected its boundaries. Protected racks offered no benefit to ammunition left outside them. The final layer of survivability was therefore human behavior. Steel established the possibility. Crew discipline preserved it. The liquid inside wet ammunition racks became less important than its famous name suggested. Wartime engineers tested how the protective system reacted to damage. They examined whether liquid actually suppressed ignition around penetrated cartridges. The results did not answer every question cleanly. A violent direct strike could overwhelm the jackets immediately. Liquid escaped when a container was punctured. A fragment could ignite propellant before enough fluid reached the damaged area. Some fires developed beyond the system's ability to control them. These limitations encouraged doubts about the liquid component. The racks still performed well as protected storage. That made the source of improvement difficult to isolate. Was the decisive factor the water mixture? Was it the armored cover? Was it the lower position beneath the turret floor? The battlefield package combined all three. Later experience increasingly emphasized location and protection. A cartridge that fragments never touched required no liquid suppression. This did not mean the wartime design had been foolish. Engineers worked with incomplete evidence and urgent deadlines. They faced a known pattern of catastrophic fires. Adding a fire-suppressing jacket was a reasonable defensive layer. It required no electronic sensor or complicated crew action. The system remained ready while the tank operated. It could function during the confused seconds after penetration. Redundant protection was valuable precisely because no single measure was certain. The design also had to operate across different climates. Water alone would freeze during European winters. The mixture therefore needed antifreeze properties. Leaks required attention. Damaged racks needed servicing. The liquid added weight and maintenance without increasing firepower. Every protective feature competed against the tank's carrying capacity. Post-war development eventually abandoned wet jackets in later Sherman modifications. That decision is sometimes presented as proof that wet stowage never worked. It proved something narrower. The liquid could be removed while retaining safer ammunition placement. Designers had learned which parts of the arrangement offered lasting value. Technology often advances through such separation. An early solution combines several ideas. Service experience reveals which ones carry most of the benefit. Later designs keep the useful geometry and discard unnecessary complexity. The Sherman's ammunition redesign followed that pattern. Its true inheritance was not a particular water mixture. It was the principle of controlling what happens after armor penetration. Later, armored vehicles pursued this principle more aggressively. Ammunition could be isolated from the crew. Armored doors could separate ready rounds from the fighting compartment. Pressure could be directed away through weaker roof panels. Automatic fire suppression could detect heat and react quickly. These systems went beyond anything available in the wartime Sherman. Their purpose remained familiar: prevent a damaged cartridge from destroying the crew compartment. The Sherman represented an intermediate stage. Its ammunition still shared the main hull with the crew. Its armored covers were not a fully isolated magazine. Its liquid jackets could not redirect a major ammunition blast, yet the move downward reduced exposure substantially. That achievement deserves precise language. Wet stowage did not stop Sherman tanks from burning. It reduced the probability of ammunition fires after penetration. It did so most effectively through relocation, enclosure, and disciplined storage. The distinction matters because exaggerated praise creates another myth. Calling the system perfect hides tanks that still burned. It ignores crews lost despite later protection. It also prevents understanding why the design worked. A magical liquid teaches nothing. A changed fragment path teaches a general engineering lesson. Survivability depends upon sequences. An enemy projectile first reaches the armor. If it penetrates, fragments enter the hull. Those fragments encounter equipment, fuel, ammunition, and people. Each object can absorb, redirect, or amplify damage. The early Sherman placed propellant near a common path. The later arrangement moved it away and added barriers that altered the sequence without changing the enemy weapon. This was a quiet form of protection. It produced no larger silhouette and no impressive gun. Most observers could not see it from outside. Even many crewmen knew the practical result more clearly than the mechanism. Their later tank was less likely to become an immediate furnace. The historical nickname remained attached to the entire Sherman family. The engineering record shows a moving target. A weakness was observed. An interim plate was installed. A deeper redesign relocated the hazard. Field evidence then tested the result. Finally, later engineers separated the useful principle from the expendable feature. That progression matters more than the nickname. It shows a mass-produced weapon learning during war. The Sherman's reputation was built from visible wrecks. Its improvement was hidden beneath an armored floor. Engineers did not make penetration impossible. They changed what a penetrating projectile was likely to strike. Ammunition moved away from vulnerable upper hull sides. Protective covers and liquid jackets added further barriers. Larger hatches improved the crew's chance of escaping. The result was not an invulnerable tank. It was a more survivable one. The lesson extended beyond one vehicle and one war. Armor protects only until armor fails. After that moment, internal arrangement decides what happens next. For later Shermans, the smallest visible change produced the largest human difference. More crews received time. More damaged tanks remained recoverable. Fewer penetrations became immediate fires. The solution was never simply water. It was better engineering beneath the crew. MOTA COW2 Sherman Tank Military History. Why did early M4 Sherman tanks develop a fearsome reputation for burning, and what changed in later production models? This documentary examines the real vulnerability behind many Sherman fires. Instead of focusing only on gasoline engines, it follows the evidence toward exposed ammunition racks inside early dry-stowage variants. It then explores the quick-fix armor program. The development of protected floor racks, liquid-filled jackets, larger crew hatches, and the arrival of wet-stowage Shermans during 1944. The story reveals why moving ammunition below the turret floor mattered more than the famous liquid surrounding it. It also explains the limits of wartime burn rate statistics, the dangers of loose ammunition, and the difference between preventing penetration and surviving what happened afterward. This documentary uses AI-assisted historical reconstructions for visual illustration. The black and white images shown in the video are not authentic archival photographs unless specifically identified. The narration is based on historical records and authoritative sources. Timeline: 0 The fire inside. 03:45 evidence from North Africa. 07:35 moving the ammunition. 11:45 wet-stowage variants. 15:50 what the burn rates reveal. 20:05 seconds to escape. 24:20 factory design versus crew practice. 28:40 was the liquid essential. 33:55 the hidden survivability lesson. M4 Sherman tank engineering armored warfare W2 tanks history documentary. CO video tags. M4 Sherman, Sherman tank, wet stowage, World War II tanks, tank ammunition fires, armored vehicle survivability, military engineering, Sherman fire myth W2 documentary. Tank history. Thumbnail. Text thumbnail tiếng Anh. The real fire risk. Nghĩa tiếng Việt nguy cơ cháy thực sự. Yêu cầu tổng hợp. Thumbnail tỷ lệ ISO, độ phân giải, Nike Page. Mang phong cách ảnh phóng viên quân sự Mỹ năm 1943. Hero duy nhất là một xe tăng M4 Sherman phiên bản dry stowage đời đầu đang được nhóm kỹ thuật quân khí kiểm tra. Bằng chứng duy nhất là cụm đạn pháo 75mm, đặt thẳng đứng trong giá đạn Sponson phía trên xích xe, được nhìn thấy qua cửa kiểm tra mở bên hông khoang chiến đấu. Cụm chữ The Real Fire Risk phải in hoa màu đỏ đậm, font đậm và hẹp đặt trực tiếp trên vùng trống bên trái ảnh. Chữ chiếm khoảng 30% chiều rộng và 20% chiều cao ảnh, có viền trắng mảnh và shadow nhẹ, không có hộp hoặc banner. Chỉ dùng đúng một vòng tròn đỏ khoanh sát một cụm vỏ đạn trong giá Sponson. Vòng tròn không được khoanh toàn bộ xe tăng. Chỉ dùng đúng một mũi tên đỏ bắt đầu từ vùng trống phía trên bên phải và kết thúc chính xác bên trong vòng tròn. Vòng tròn và mũi tên có viền trắng mảnh. Ảnh đen trắng thật. Midtone sáng hơn ảnh lưu trữ thông thường khoảng 12%, vẫn giữ grain, độ mềm quang học, tương phản hạn chế và bố cục quan sát tự nhiên. Prompt thumbnail hoàn chỉnh. Create a historically accurate YouTube documentary thumbnail in 16:9 format at exactly 1920 1080. Depict a candid United States Army Ordnance inspection during 1943. Centered on one early production dry stowage M4 Sherman medium tank. Show the tank from a close 3/4 side angle inside a simple field maintenance area. An open side inspection access point must reveal one specific rack of vertically stored 75mm cartridges in the upper hull sponson above the track. The ammunition rack is the only technical evidence emphasized. Include 2 United States Army Ordnance mechanics in accurate 1943 work uniforms naturally examining the open compartment. They must concentrate on the machinery and must not look toward the camera. Use true black and white with a silver gelatin tonal response, subtle film grain, slight optical softness, restrained contrast, limited dynamic range, authentic steel wear, natural imperfect framing, and credible wartime photojournalism. Brighten the midtones by approximately 12% for mobile readability, while preserving period photographic character. Place the exact uppercase text, The Real Fire Risk, directly on the empty left side of the image. Render the text in deep red using one bold condensed typeface. Make the text group occupy approximately 30% of the image width and 20% of its height. Add one thin white outline and a subtle shadow to the entire text group. Do not use a box, banner, plate, gradient, or colored background behind the text. Add exactly one deep red circle with a thin white outline. The circle must tightly surround only one small cluster of 75mm cartridge cases inside the exposed sponson rack. Leave approximately 8% visual margin between the target and the circle. Do not circle the entire tank, hull, track, mechanic, or compartment. Add exactly one deep red arrow with a thin white outline. Begin the arrow in unused space near the upper right. End its point precisely inside the single red circle on the exposed cartridges. Do not add any second circle, second arrow, decorative symbol, caption, insignia, or random text. Keep the Sherman as the single hero and the exposed ammunition rack as the single piece of evidence. Avoid poster composition, heroic posing, modern cinematic lighting, AI art appearance. CGI, digital painting, game render aesthetics, excessive sharpness, modern tools, inaccurate ammunition, distorted machinery, duplicated people, repeated faces, malformed hands, impossible shadows, gore bodies, or graphic injuries.